Thank you for joining us today on the Anesthesia and Perioperative Medicine channel. Obrigada por nos acompanhar hoje no canal de Anestesia e Medicina Perioperatória. Tak fordi du deltager I dag på kanalen for anæstesi og perioperativ medicin. 感谢您今天收看麻醉与微手术器医学频道。All right, everyone. Today, we are going to tackle a topic that is moving right out of science fiction and into very real conversations about the future of our operating rooms, fully autonomous surgical robots. Now, in this explainer, we're going to break down the tech, get real about the huge clinical challenges, and most importantly for us, we're going to explore how this is going to reshape not just the role of the surgeon, but our own role as anesthesiologists. You know, this quote from Axel Krieger, who's one of the lead researchers on a breakthrough we're about to discuss, it just hits the nail on the head. This really captures the massive shift we're talking about. We're moving beyond the robot as just a fancier, more stable tool. We're now talking about a machine that can actually understand the flow of a procedure, and that is a whole different ballgame. But that brings up the absolute critical question for everyone in our field, right? What does understanding a surgery even mean to a machine when the only thing that really matters is the patient's physiology second by second? A state that, let's be honest, only we are truly watching from start to finish. That question is going to be the lens through which we look at everything today. So here's our game plan. We're going to walk through 6 key parts. We'll kick things off with a big breakthrough in the lab. Then, we're going to do a serious reality check on what's happening in our ORs today. We'll break down the 4 huge barriers holding this back, and then look ahead to what this means for surgeons, and of course, for us as the safety gatekeepers. We'll wrap up with a roadmap for the next 10 years. Okay, let's dive right into part 1, the groundbreaking experiment that really got this whole conversation started and has everyone in the field talking. So picture this. Researchers at Johns Hopkins release a paper about their robot, the SRT-H. This machine successfully performed a full cholecystectomy, a gallbladder removal, completely on its own. Now, the huge asterisk here is that this was ex vivo, on organs from deceased pigs, not a living, breathing patient. But still, the achievement was absolutely stunning. The robot executed a complex 17-step procedure from start to finish with no human touching the controls. And it nailed it, 100% success rate over 8 tries. The how is just as wild. They didn't program it with rigid step-by-step instructions. Instead, the AI learned by watching videos of human surgeons, kind of like how ChatGPT learns to write by reading the internet. It's a method called imitation learning, and it's what gives it that sense of understanding. So, how did it actually stack up against a human? Well, as you'd expect, it was slower. No surprise there. But check this out. Its movements were actually smoother, less jerky, and its toolpaths, the routes it took from point A to point B, were more efficient, shorter, and more optimized. But here's the real jaw-dropper. Its adaptability. When things looked a little different from what it expected, it would self-correct its plan, on average 6 times per surgery, all without help. That's not just a pre-programmed machine. That's rudimentary problem solving. That lab result is incredible, and it absolutely points to where we're headed. But let's all take a deep breath and come back down to earth for a minute. We need a serious reality check, because the gap between that lab experiment and the Da Vinci sitting in OR3 is, well, it's vast. So in part 2, let's deconstruct the hype and talk about what robotic surgery actually means today. And this is probably the single most important distinction we need to make. When we talk about doing a robotic case, what we're really talking about is a teleoperated procedure. The robot is not making a single decision. Think of it as the world's most advanced puppet. The surgeon is the puppet master, sitting at a console, and every single move, every cut is a direct translation of their hands. The robot has 0 autonomy. It's an amazing tool, but it's just that, a tool. And speaking of those tools, wow, just look at this market. It's basically a one-company show right now. Intuitive Surgical, the company that makes the Da Vinci system, has an absolute stranglehold on the market with a staggering 78% share. That kind of dominance has huge implications for how and how fast this technology develops. And that market share is backed by a mountain of cash. I mean, look at these numbers. A market cap hovering near $200 billion, and a PE ratio in the 70s means that investors are betting huge on their future growth. What this means for hospitals is a powerful lock-in effect. Once your institution buys a Da Vinci, you're in their whole ecosystem of instruments and service contracts, which makes it really hard to even consider switching. This brings us to a really crucial point about philosophy. The whole development path for intuitive surgical is focused on what they call surgeon autonomy. Their new Da Vinci 5 is all about making the human surgeon better, giving them better force feedback, better visuals. It's all about empowering the human. The SRT-H robot from the lab, on the other hand, is about robot autonomy. The goal there is to have the robot act as a skilled assistant, doing things independently. These are two fundamentally different paths. To make sense of this journey, people use this framework of 6 levels of autonomy, kind of like we do for self-driving cars. Level 0 is just standard manual surgery. The Da Vinci 5 we use today, that's firmly at level 1, maybe level 1.5 if you're being generous. We're just now starting to see some level 2 things, like an AI-guided camera. And that amazing Johns Hopkins experiment, that was a demonstration of level 3. So as you can see, we have a very, very long way to go to get to levels 4 and 5. So if the research is already demonstrating level 3, you have to be asking, well, why isn't this in my OR next week? And that's the multi-billion-dollar question. The answer is that the barriers to get from the lab to a live patient are just immense. And that's what we're going to break down now in part 3. You can really group these roadblocks into 4 big buckets. You've got the technical and data problems, you've got the huge regulatory wall, there's a complete legal and ethical black hole, and finally, there's just the challenge of clinical acceptance. Let's walk through each one. First, the technical stuff. And you and I know this better than anyone. Patients are messy. They are not standardized parts in an assembly line. An AI can learn from a perfect textbook anatomy, but what happens when it encounters a patient with a wall of adhesions from 3 previous surgeries? What does it do when cautery smoke completely obscures the camera? Not to mention, it has no sense of touch. It can't feel that tissue is under too much tension. And maybe the biggest problem of all, how do you teach an AI what not to do without a huge database of surgical errors for it to learn from? It's a massive challenge. Next up, the regulatory wall, and this is a big one. The whole point of modern AI is that it learns and gets better over time. But the entire foundation of FDA device approval is that a device must be fixed and predictable. Its behavior can't change from the day it's approved. A learning, evolving AI is, by its very definition, not fixed. This isn't just a hurdle. It's a fundamental philosophical conflict with the way we regulate medical devices. Okay, and let's say we somehow solve the technical and regulatory problems. We then run into a complete legal and ethical void. If the autonomous robot makes a mistake that harms a patient, who gets sued? Is it the surgeon who is supervising from a console, the hospital, the manufacturer, the software engineer who wrote the algorithm? Our legal system has absolutely no framework for this, which makes things like malpractice insurance nearly impossible to figure out. But let's fast forward 10 or 20 years and assume that we start to slowly overcome these barriers. What does the OR actually look like? In part 4, let's start with the most obvious change, the role of the surgeon. It's going to be completely transformed. The fundamental idea is that a surgeon's value will shift from their hands to their head. It becomes less about their raw technical skill in manipulating instruments and much more about their ability to do strategic planning, oversee the system, and, most critically, to be the expert crisis manager when things go off the rails. So this creates a whole new paradigm. The surgeon goes from being the executive surgeon to the strategic supervisor. You can imagine a future where one senior surgeon sits in a control room overseeing maybe 3 or 4 routine standardized procedures like hernia repairs happening at the same time. This could be a massive win for hospital efficiency. But just think about what that does to surgical training. The focus of residency would have to shift dramatically away from repetitive motor skills towards systems management and emergency protocols. So if the surgeon's role is shifting to that of a supervisor, that leads us directly to part 5. And for me, this is the absolute heart of the matter for our specialty. Because in an autonomous OR, the ultimate real-time responsibility for patient safety is going to fall squarely on our shoulders. We become the final human safety gatekeeper.
And to do that job effectively, we will need to formalize a concept that we can call situational authority. This has to be a clearly defined, protocol-driven power that allows us to unilaterally pause or completely stop the robot, based on our interpretation of the physiological data. This isn't about asking the surgeon for permission. It's an executive command. We have to be the ultimate human in the loop.
And here is the fundamental reason why. The robot has a perfect high-definition 3D view of the anatomy. The supervising surgeon, maybe in another room, is overseeing the surgical plan. But we are the only ones at the head of the bed, synthesizing the complete physiological picture of the patient. The robot doesn't understand the meaning of a dropping end-tidal CO2 or a rising pressure requirement. It sees anatomy. We see pathophysiology. Okay, let's make this really concrete. Look at these scenarios. In scenario 1, there's a slow, hidden venous bleed. To the robot, the field of view is clear, so it just keeps working. It thinks everything is green. But on our monitor, we're seeing the map trend down, the ETCO2 fall, the robot is green, but the patient is red. That's when we have to exercise our veto and pause the procedure. Or think about anaphylaxis. The robot is happily dissecting tissue, completely unaware, while we are dealing with a sudden desat and can't ventilate the patient. That's not a pause, that's an immediate emergency stop. In every one of these cases, we are the only ones who can prevent a catastrophe. Because of those risks, these safety protocols aren't just suggestions. They are the absolute minimum requirements for any hospital considering this technology. We must have a literal or digital big red button that gives us unilateral emergency stop authority. And beyond that, the system itself has to have automated pauses, let's call them physiology-triggered pauses, that are hard-coded and linked to our monitors. A map below a certain threshold for a set amount of time, the robot stops, period. These automated safety nets, governed by anesthesia, are the foundation of patient safety. So, this future isn't going to arrive all at once. It's going to be a slow, cautious evolution over the next decade at least. So, in our final section, let's talk about the roadmap. How do we and our hospitals actually prepare for this transformation? Well, adoption won't be uniform. You're going to see it start in very specific places. Big academic medical centers will be the test beds for research and validation. High-volume surgical centers that already do tons of standardized procedures will be the first to adopt it to drive efficiency. And you might even see it in smaller specialty clinics like a dedicated hernia center, because their cases are so predictable, which is the perfect environment to generate the clean data needed to train an AI. So if you map this out over the next 10 years, it'll likely be a phased approach. For the next 1 to 3 years, expect to see more level 2 task automation. Things like smarter cameras or maybe an autonomous suturing tool, always with direct supervision. In the 4 to 6 year time frame, we might see the first autonomous modules for specific, standardized parts of a common surgery. And the real deal, a full, low-risk procedure done autonomously from start to finish, we're probably talking 7 to 10 years out. And even then, it would be in closely monitored clinical trials with highly selected, ideal patients. So let's wrap this up. This technological shift, as slow as it may be, feels inevitable. And that leaves our specialty with one final and I think incredibly important question. The autonomous OR is coming. When your hospital decides to write the safety protocols for it, who is going to be at that table? If we are passive, those rules will be written for us, by engineers, by administrators. The imperative for us, as the guardians of patient physiology, is to lead this conversation. The answer to this question must be, we will. Thank you for your time.